Good morning. In yesterday's class, we were looking at interference and we looked at the conditions which are required to have interference, so the conditions on the source. Particularly, we looked at the coherence properties that are required. And then we said we are going to focus on sources which we assume have good spatial and temporal coherence, and arrived at an expression for the interference intensity when you interfere two beams which have been derived from the same source. Okay? And the expression we had was this expression here, where I1 was the intensity of one of the beams that was being interfered, I2 was the intensity of the second beam, and the third term, and that's the interesting term, which is also a function of both these intensities, but more importantly has a phase factor to it, and that phase is a function of the phase difference between the two beams that are participating in this interference. Okay. So, this delta is nothing but the path length difference, or the phase relating to the path length difference of the two beams that are interfering. How do you think we can use this? Why is phase important? Or where do we use this? Where do we use interference? I started yesterday's class showing you some pictures, right? We had a pattern of which you could see if you have an oil on the road, a oil patch on the road, you see these nice colorful fringes. Right? So you observe interference. But why is it useful? What application do you know, or what could you think of where this is useful? We're measuring phase, we could potentially measure phase, and we know phase, I've said this is delta, it relates to the phase, which delta is the phase which relates to the optical path length difference. Where is that useful?
Constructive interference depends on phase only, you will get the constructive and destructive interference.
Okay, how is that useful to? So he's saying that you get constructive or destructive interference. That is what gives you the fringe pattern, right? But how is that useful is my question. Yes, I get a fringe pattern, right? We saw that those pictures I showed you yesterday, those were fringe patterns. Because the source was white light, your fringe pattern was colored. You had some regions where constructive interference happens for one wavelength, and in other places it happens for another wavelength. So wherever you had constructive interference for a particular wavelength, you had a fringe of that color. How is that useful? Or is interference something which we say, oh, it makes pretty patterns, that's nice, and we leave it at that? It's just something that we can admire, we can understand, we can appreciate its beauty, but there is no other purpose to it. Where do you think? Ask this question in a scientific way, because if I say I want to use interference, well, from interference presumably I can somehow get phase. And what do I relate phase to, and what could I possibly extract from that? Pardon? So he says refractive index of a medium, and that is correct. That is one of the possible things that you can extract. What else could you extract? If you say refractive index, you must immediately say something else. Pardon? Thickness. So basically phase relates to path length, right? Optical path length. We know this. We should know this very well by now, right? So if I say I have a phase phi, it is 2 pi by lambda into NL. Now if somehow, so what does interference allow me to do? It converts this phase into an intensity. That is really why the interferometer is such a powerful instrument or method of measurement, because, so how do we see something? If I'm talking about a person, we use our eyes to see. So our eyes are our detectors. If we are running an experiment or you're using your phone, you have a camera and the camera has a sensor. Now, whether it's our sensor, the retina of our eye, or whether it's the sensor of a measurement system like a camera, so a CCD sensor or a CMOS sensor, do these respond to phase or intensity or both? Does our retina respond to phase? Does a CMOS sensor respond to phase? Or does it respond to intensity and phase? Or does it respond only to intensity? These detectors respond only to intensity, right? So whether the detector is our eye, so the detectors that we commonly use, and that means our eye or a CCD or a CMOS, all of these respond to intensity. They don't respond to phase. So if I have two beams of equal intensity or the same intensity distribution, but they have a different phase pattern over them, and I were to illuminate a CCD array with first the one beam and then the other, I wouldn't be able to tell the difference. As far as the sensor is concerned, they're the same because the intensity distribution is the same. If I want to see phase, I have to do something different to see phase. And what do? We do interference. That is what allows us to see phase. So this allows us to see phase. I still don't know exactly how I'm going to get the phase. I'm telling you it allows us to see phase, but the CCD array is still responding to intensity. So if I were to have, if this could be, I've just written I like this, but it could be a function of xy. So it means there's a intensity distribution. Okay, the CCD array is measuring I of xy. So I can say that the intensity at various positions has this value. I still haven't measured phase directly. If somehow I can use this expression, I may be able to extract this delta. Okay, and we're in this class going to figure out how that's possible. If I get that value of delta, then and I've written it here as phase. So basically this is the phase. It doesn't matter what parameter I use. So this is the phase. If I measure the phase and I know the wavelength that I'm working with, then I can extract the optical path length, right? So we're doing this step by step, and it has to be step by step. It's not that I'm interested in measuring phase and then I put in a sensor and here's the phase, right? I want to measure phase. In order to do that, I can't even just measure intensity, right? I do an interference pattern so that the phase of interest lies in this third term, and we'll see why. Why can't I just illuminate? If I'm going to use some indirect method by which to measure phase, why can't I just take a beam which is a exponential j phi, take the square of this so that I get the intensity and extract phase directly from this, right? But if you think about it, what is the intensity of this beam? So what is the question that I'm asking you? Our goal, and we'll see why, is to measure phase. No known detector directly measures phase. So we are going to measure phase through the measurement of intensity. Okay. Now I am saying we need some indirect way of taking phase or extracting phase out of that intensity measurement. Why can't I just shine the beam whose phase I want directly onto, if I have an indirect way, why wouldn't I just shine the beam directly and use that indirect method and get the phase out? This, what I've written over here, is amplitude. What is the detector measuring? It's not measuring amplitude, right? It's measuring intensity. What's the intensity of this expression? I've lost the phase information, right? That's why you have to carry out an interference, because the interference gives me this expression. I have still, in a sense, lost the phase, because what you are measuring is this. But this is a function of this. And we are going to see the way we extract it. Because I've carried out an interference, I am able to go and get out that delta. Okay? So, in order to get optical path length, I am getting phase. In order to get phase, I am doing an interference. Okay? Now, again, I am saying I get optical path length. That means if I somehow measure phase, I can get the product n into L. This is of course assuming you know lambda. And if I want to use this, say, to measure the refractive index of some unknown medium, I then need to know the thickness of that medium, and then I'll be able to calculate what is the value of n. Or I might know the refractive index of that medium, and I want to find out what happens, what is the optical thickness, and therefore I would substitute n and find out n, right? It is so powerful a technique, because it's not just simply that I want to measure n or I want to measure L, but I can use this as a sensor. Let's say there's a temperature change, okay? And let's say the temperature changes are small enough that I can make the assumption of, for the particular material I'm looking at, the n doesn't change with the temperature change, but the L changes. That means the material expands or contracts. Now, if I can make some assumption about n, I can, from the change in the optical path length, I can find out the change in L. From the change in L, I can find out the change in the temperature, or maybe the change in pressure, or the change in some parameter. Okay? So, I can use this as a sensor. So, I am interested in phase because buried in phase is information, and that is what we are always trying to do. We are trying to build a system, or we are trying to build systems that we can use to extract information.